All right. Good morning, everyone, and welcome and thank you for joining the Modern Community Practice monthly webinar. My name is Chatty Chen. I'm with the Modern Support Team, Environmental Knowledge and Prediction Branch of Resource Stewardship Division of Alberta Environment and Parks. And today, we are very fortunate to have Dr. Saman Razavi to come to talk to us. And actually, Dr. Razavi, he is now in UK, so we really appreciate that he still takes time to give us a talk. And yeah, today's talk, the topic, actually the interesting topic is Anthropocene flooding, challenge for science and society. So this is going to be very interesting talk. And so Dr. Razavi, he's the abstract of his presentation and his bio is in the meeting invite, so I don't need to go through again. And he is the associate professor of the hydrology and water resource engineering at the School of Environment and the Sustainability of University of Saskatchewan. And so today's webinar with the Dr. Razavi's permission, so the PowerPoint slide in PDF will be shared afterwards. And also this webinar is recorded and will be shared after the presentation as well. And so just a few housekeeping items. So for the question, and you can ask questions, just post on the chat box and we are monitoring that. And or you can actually, after Dr. Razavi's presentation, and there will be a quick question and response time, so you can actually ask a question directly to the presenter. And just to remind folks, just mute your microphone and to minimize the potential interference. And as thank you for your cooperation. So with that, let's give the Dr. Razavi a virtual round of applause. And welcome, Dr. Razavi, and you can go ahead, Dr. Razavi.
Thank you, Chiadi. Do you hear me well?
Yes, so good. Yes.
Hey, hello, everyone. My name is Saman Razavi, Associate Professor, University of Saskatchewan. And yes, I'm now in the UK, Birmingham, and I arrived a couple of days ago. I'm traveling overseas after almost 2 years. Who can believe it? Anyways, it has been stressful, but I'm now here staying for the rest of this month, working with some colleagues at this university, University of Birmingham. Anyways, it's 6 p.m. here. I'm very excited to be with you, and thank you very much for the opportunity and the invite and everything. You might know that I'm an engineer and hydrologist. So while I'm here to talk about floods, I understand that floods and flood disasters are complex, many faceted issues, and I don't think I'm really an expert in them. So naturally, I only can look into certain aspects of floods, and I'm not a social scientist, but I understand that socioeconomic aspects of floods are also quite important and often ignored by engineers like me. So that is something that I've been trying to work on and collaborating with my social scientist, economist colleagues in general. So I return the curiosity about these things, other disciplines, and trying to look at the interface of science of floods and science on water in general, the public and policy. Before I begin, I just wanted to say that I have had the privilege to work with a number of folks at Alberta Environments and Parks, and I'm very thankful to all the collaborations and insights that I have received through these collaborations. Especially, I'm thankful to Dr. Khaled Akhtar from AEP for the invite to give this talk. Khaled is also, you might know, he's an adjunct professor in my school, and we're thankful for his continued contributions and support to our programs, particularly to our major research program called Global Water Futures and Integrated Modeling Program for Canada. So with that intro, let me begin with a global context and some of the disastrous threats to people around the world, data from all around the world show that the frequency of some types of disastrous hazards has increased significantly over the past few decades. Most notable is flooding, to the point where flooding is now the most common type of natural hazard. In addition to floods and storms, risk to humans due to extreme temperature, drought, and particularly wildfire have been increasing. And just to be clear, so this data that I'm showing is from an international disaster database, and to qualify for a disastrous event, an event should have one of the following criteria: 10 or more people dead, 100 or more people affected, the declaration of state of emergency, or a call for international assistance. Let's come home to Canada. Of course, we've had and still get all sorts of natural hazards that cost us billions of dollars and a lot of non-monetary damages. Almost every other year, we get a major flood somewhere in the country. In Calgary, you must remember floods in 2013. Extreme wildfires are also bitter reality now, affecting many Canadians, particularly in Western Canada. And drought. Just this past summer, many farmers in the prairie were suffering from lack of rain. We also get all sorts of water quality issues, particularly in our rural and remote communities. And we typically attribute these escalating issues to global warming and climate change because we're observing their creeping impacts. Just in Western Canada, our winters have increased in temperature by more than 6 degrees Celsius. And as a result, our permafrost regions are thawing, our glaciers are retreating with significant but very gradual damages to our infrastructure and the environment. So sure, all of this is true, but only part of the story. And that's kind of the message that this talk tries to convey. To elaborate on this message that I'm trying to say and motivate the discussion, I would like to share with you a story, actually a series of real events in Australia that caught my attention in early 2019, when a very active monsoon system created unprecedented rainfall for the Queensland coast of Australia in January and February. It was after a hot and dry period, and perhaps like every other year, a reservoir there named Ross River Dam was filling in January to store water to meet demands later in the year. Then the unprecedented rainfall hit, and with more than 1 meters of rain in a week, a year's worth of rain, the dam got filled very quickly and reached the emergency level. And the operators ended up fully opening all the gates for dam safety issues. So what happened next? The downstream city called Townsville got flooded, resulting in 5 casualties and more than $1.2 billion in property damages, and of course, significant indirect costs and consequences that are always hard to quantify in monetary terms. Of course, the public reaction was very serious. I'm quoting from The Guardian, for example, that some residents have expressed anger that water was allowed to build for so long rather than be released more steadily during the previous week of the continued heavy monsoonal rain. And as a result of the public anger, dam management went under scrutiny. Anyways, the situation further escalated and became political to a point that involved the Premier of Queensland. But from an engineering perspective, operational protocols were up to date and followed. Basically, the emergency action plan was updated in 2018, just 1 year before the flood, in which floods similar in magnitude to the 2019 flood had been analyzed. So what was wrong then? perhaps the issues were well beyond operational rules that govern day-to-day decision-making. Perhaps the issue arises from deeper, more fundamental dimensions associated with infrastructure planning and design, human settlement in the floodplain, and perceptions of risk, and basically the often ignored aspects in the co-evolution history of natural social environments. For example, the Ross River Dam was constructed in 1974 for Townsville flood protection, but it led to significant population growth in the downstream floodplain, where residents depended on that dam for water supply. So the dam purpose had quietly shifted from primarily flood control to flood control and water supply, two objectives that are naturally conflicting. One outcome of these societal changes was that many flooded properties were uninsured because they were considered to be in flood-free zones. And eventually the big surprise arrived and the unprecedented rainfall hit, and the rest is history. Of course, what I just said is a common story, not unique to the Townsville flood. You might remember the floods of April 2019 in Ottawa River Basin, which is regulated by a series of reservoirs. That event produced record-breaking flood peaks in Ottawa and Gatineau and surrounding communities. And similar to Townsville flood, there was a lot of public concerns around the operation of reservoirs in this basin, and even some conspiracy theories. And as a result, reservoir operations went under scrutiny. Or in May 2019, record-breaking flood occurred across the Mississippi River Basin, a heavily managed water system. Local residents back then blamed the US Army Corps of Engineers for the mismanagement of hundreds of reservoirs. Or in Iran that year, there were deadly floods, some in areas where major rivers are managed by dams and reservoirs. Many Iranians wondered why the many existing dams and infrastructure were unable to protect them from those floods. I think the message is that the growth of disastrous events, particularly in regions with extensive engineering and infrastructure, challenges the current science policy paradigms and undermines the public trust in the engineering enterprise. For me, this is due to two general but interrelated challenges. First, deep and profound uncertainty on how the future might look like, so we can plan or adapt to it. A major source of uncertainty is, of course, the climate change and its implications for our lands, hydrology, freeze-thaw cycles, and so on. And added to that are major uncertainties due to technological, societal, and political changes. These drivers directly affect how we operate and manage our water resources and the environment. And second is the complexity of the problems that we need to deal with and the trade-offs that they present. Natural, engineered, and social systems are interwoven in complex ways, connected through feedback mechanisms that are often hard to quantify and predict, but can result in cascading or spin-off effects that are ignored in traditional engineering approaches. We deal with a range of conflicting interests and trade-offs. I just gave an example of flood versus water supply. But our typical cost-benefit analysis can only focus on a small subset of them and often ignore the rest, particularly social damage costs, including public unrest, loss of lives, and long-term adverse effects on mental health are typically excluded from economic impact assessments because they are hard to quantify in monetary terms. And all these are further complicated by time-varying nature and perceptions of values and risk at individual, community, and institutional levels. These changes are linked to socioeconomic interests that are hard to quantify and are affected by social memories of prior floods and droughts and also media. So what do we do with respect to these challenges? Our research work and vision can be broken into 4 themes. In theme A, that we call integrated earth systems modeling, we try to improve and integrate models of natural systems, such as climate and hydrology, to provide tools to address modeling uncertainties. In theme B, called water management modeling, coupling human-driven and natural systems, we try to develop and integrate water resources models with assessment tools to explore ecosystem constraints and economic trade-offs of water decisions and development. In theme C, sorry, I went ahead of myself. In theme C, called decision-making under uncertainty and non-stationarity, we try to use our models in support of decision and policy making. And in theme D, at the center, called user engagement and knowledge mobilization, we try to involve stakeholders and collaborators in the research process. And I should say we've been very lucky to have been able to bring these 4 pieces together in a fairly large project under the framework of Global Water Futures that started in 2017 and named Integrated Modeling Program for Canada, or IMPC in short. And we assembled an interdisciplinary team of investigators across 5 Canadian universities. They come from backgrounds in engineering, natural sciences, social sciences, economics, and computer science. And we have partnered with a range of collaborators, including Alberta Environments and Parks. And yeah, here we are. And of course, some of you are already involved. And for more information, if interested, you could refer to our website. So what do we exactly do? In the following, I'm going to present some pieces of our recent work and how they come together. We've been contributing to earth systems modeling with an emphasis on land surface and hydrology, and using a wide range of ground-based data and various remote sensing and satellite data to build models that simulate different variables across watersheds over time, such as soil moisture, evaporation, and runoff. Most of our work on hydrologic modeling has been with the mesh land surface hydrology modeling system in close collaboration with Environment and Climate Change Canada under a major research program called the Changing Cold Region Network, CCRN, that ended a couple of years ago. And MESH is not only a hydrologic model, it can also be coupled with climate models. So technically it can be the lower boundary condition of atmospheric climate models as well. And in brief, it is based on CLASS, Canadian Land Surface Scheme, to represent the vertical energy and water balance processes through soil and vegetation. It also has multiple modules to represent lateral processes in a grid cell and routing module between the grid cells and across the basin. So we've contributed to addressing parameter and model structural uncertainty, representation of soil processes in cold regions, in particular in permafrost regions, freeze-thaw and memory in permafrost, and also addressing uncertainty in input data, particularly precipitation. As you know, precipitation is one of the most, or the biggest source of uncertainty for us in Canada because our gauging network is actually quite sparse. And to do so, we've been looking at various sources like GPM satellites. So we have coupled our hydrologic model with state-of-the-art atmospheric model called WRF, developed by my atmospheric scientist colleague Yan-Ping Li at the Global Institute for Water Security, University of Saskatchewan. And this way we are able to represent convective storms, which are major driver of flash floods in the prairie. Here I'm showing the performance of this coupled model in simulating the historical hydrograph of the Bow River at Banff over a 15-year period. And as you see, the model does well in capturing the peak of the Calgary 2013 flood, which is generally a hard thing to do. And in the table to the left, I'm showing some example projections for the same basin for the last 15 years of the century using the coupled model and based on a pseudo global warming dynamical downscaling method. For example, according to this projection, the annual precipitation in this basin will increase by 13%. Average temperature will increase by more than 4 degrees Celsius. And the rainfall to total precipitation ratio will increase from 0.3 to 0.48. And these results help us, and of course, and we're going to see an increase in runoff as well. These results help us better understand how much sustainable water and how and when we will be available for our various water demands in the basin. But what I just described with modeling is only one half of the story. We already know that the human interventions to the natural systems is profound. We have changed the natural regimes in watersheds by building dams, diversions, irrigations, and so on. For example, the flow regime in the South Saskatchewan River, where I live, has significantly changed after building the Gardiner Dam and other water infrastructure upstream. Average of flow peaks in summertime has reduced to less than 1/2, while low flows in winter have almost tripled. And by building dams and reservoirs and irrigation and treatment plants and etc., we try to control floods, mitigate droughts, and supply water for a range of water supply for a range of water demands like domestic, hydropower, industrial, agricultural demands, and so on. But doing this process right is critical for building resilience, particularly against climate change and its impacts. So to do it right, we need to see atmosphere, hydrology, and water management all in a unified, integrated modeling and management framework to preserve and represent interactions and feedback mechanisms across various components of the human natural system, and also to provide a holistic view of water problems and avoid unintended consequences in decision and policy making. But doing so is not easy. The thing is, hydrologic models and water management models have quite advanced, but historically in isolation, in separate research camps. And there are a range of issues in coupling them. If you've been to the research community, so for example, AG, American Geophysical Union people have been hydrologists and have been favoring hydrology or process understanding, process representation mainly, while, for example, people attending ASC, American Society of Civil Engineers conferences, have been more favoring water management aspects, and they've been working generally in isolation. But in the last 5-10 years or so, they've started coming really together. That is very promising. So in the following slides, I'm going to try to show how we've been trying to bring the best of the two together and integrate them and why it matters. Okay, some factual information first. According to one of the most recent databases, more than 38,000 dams have already been built globally. And in the animation to the right, you can see some of them, and that the Western world started the dam building movement with full power in late 19th century, and the rest of the world gradually caught up. And still, things are uneven globally. Now there is a growing notion of dam removal in some parts of the world, particularly in the US, while in some other parts of the world, there are many more reservoirs already planned or under construction. In the Middle East, for example, the countries are still pushing the gas pedal with full power for more dams. Projects like GAP in the headwaters of Tigris and Euphrates and GERD on the Nile Basin have been making headlines recently in major news outlets. Anyways, we need to do what we need to do is to represent reservoirs in our models, which is a very hard thing to do. First of all, there is no or limited data on how many of these reservoirs are operated, even in Canada. Second, the operation of reservoirs is purpose-driven and location-specific, and therefore it's non-trivial to come up with some universal rules for their simulation. What have we done to address this? We've developed a generalized parametric reservoir operation model based on flexible zoning and piecewise linear relationships between reservoir storage, inflow, and release. And this model has shown to outperform alternatives for a range of reservoirs in Canada and globally. This model can be integrated into any hydrology land surface model at the local, regional, or global scales. We built it into the mesh modeling system, and other groups elsewhere have built it into other models, such as Raven and Parfla. Okay, that was the reservoirs, but we also need to account for other human-driven components, such as diversions, irrigation, return flows, transboundary water agreements, and so on. To do so, we have developed a system-wide water management model for the Saskatchewan River Basin. This model simulates more than 50 reservoirs, more than 25 hydropower stations, more than 150 irrigation nodes, more than 200 non-irrigation water demand nodes, environmental flows across the basin, and water rights and priorities. Now with this model, coupled with our hydrologic model, we can simulate the water resources system from local scale to large transboundary basin scale. We can optimize the operation of existing water infrastructure, such as dams and reservoirs, and we can evaluate potential or planned water infrastructure and irrigation expansion, and can assess trade-offs, such as those between irrigation and hydropower and environmental flows under a wide range of what-if scenarios. There are other aspects as well that we need to account for. There are many socioeconomic dimensions that we need to be mindful of in support of decision making. And these aspects can be beyond our traditional engineering approaches. To address this need, we've been trying to work with colleagues from social sciences and economics to develop and integrate socioeconomic models, and to also to better engage with communities, as I briefly explain in the following. So I'm just going to briefly show some of our work on hydroeconomic modeling. We worked with Brouwer, an economist out of the University of Waterloo, and co-supervised Laila Eamen, a PhD student, and she's actually recently graduated. She's now a postdoc with me under the Global Water Futures. And we did that basically to bridge the local scale water resources operations to the river basin economy. Why does it matter? Because in standard water resources systems models, we can only include economic sectors that directly use water, but they all together may be a small part of the economy. For example, in Alberta and Saskatchewan, the contribution of these sectors, water-dependent sectors, to the provincial GDP is only about 30%. But these sectors are interconnected with other sectors through intersectoral and interregional transactions. we cannot account for those in our standard engineering methods. So we developed an economic model based on input-output tables and coupled that with our water resources model to account for intersectoral and interregional interactions. Doing so can give you a new perspective on the value of water. For example, we showed at the time of drought, scenario of drought, economic losses can be reduced by almost 50% by adopting appropriate management practices, including prioritization of water allocation using alternative water sources and water reuse technologies. And another example, you might have heard of the $4 billion project for irrigation expansion in Saskatchewan that was announced at the peak of the COVID unemployment crisis in Saskatchewan in summer 2020. So of course, our model has been able to simulate this development scenario, and our model has been able to estimate the direct and indirect contributions of this project to annual gross output of different sectors in different regions. For example, roughly speaking, this project can contribute somewhere around $214 million in a year to the local economy in different sectors. Naturally, most of this, about $170 million, is the increase in irrigated crop and animal production. But as you see on the screen, it would also contribute to many other sectors, directly or indirectly. For example, $40 million to manufacturing, $1 million to transportation and warehousing, and $1 million to information and cultural industries. Quite importantly, this project can have major economic impacts on other regions as well, not locally just around the irrigation expansion, basically project, including upstream Alberta. For example, this project can add more than $70 million to the annual gross output in the Bow and Oldman subbasins in Alberta. And these are indirect impacts that come through intersectoral and interregional transactions. Of this, for example, $29 million goes to manufacturing, and that is mainly for food processing. $3 million goes to transportation and warehousing, and $1 million to information and cultural industries. And of course, the rest goes to many other sectors, economic sectors in the basin. And I should say this disclaimer that these are just rough estimates, and a more accurate estimate really requires extensive economic analysis. But these are just some rough numbers to motivate the discussion and how important it is to have an integrated modeling approach, so we can see all the indirect and indirect impacts of a policy in one region and other parts of the watershed. And also you can see the impact of that small, the impact on that small portion in Manitoba is negative -0.8, and that is because of the reduction in hydropower in Manitoba due to water withdrawals in Saskatchewan. And of course, there are some strong assumptions behind this analysis around the structure and dynamics of the economy, which are known to be invalid under certain conditions. Anyways, a point is that in classic water engineering, a general assumption is that it is always upstream that controls downstream, and that is intuitive because water flows downward. But when you bring in the socio-economic aspects, you get a more comprehensive picture. Then you can see and possibly quantify how decisions upstream decisions downstream can also have quite a bit of influence on upstream. So we've been doing this integrated modeling. One driving purpose has been to promote the dialogue between the different jurisdictions around shared waters, and with these models, people can see really the relevance of their decisions elsewhere, and also that in their own lives, and basically to zoom out from a localized view to more holistic, system-wide view of the impacts of policy. So I'm going to end this talk with a couple of ideas about future directions, particularly in my own research program. Deep uncertainty. I think there is still major underappreciation of uncertainty in our research and practice to support decision and policy making. Let me show you an example about the extent of uncertainty we have to deal with in precipitation, for example, for the Nelson-Churchill Basin, based on the full range of available climate models in the world. I'm not going to explain the nitty-gritty and just want to draw your attention to the range of uncertainty, for example, towards the end of the century, the bottom of this plot. Basically, what this plot shows us is that the average summer precipitation in Nelson-Churchill River Basin may decrease by minus 45% or increase by 15%. This is a very big range of uncertainty, and different estimates, of course, would require different policy actions. And if you provide a decision maker with such a range, they won't like you anymore. And it is not only about climate and waters, it's also about other drivers of uncertainty, such as technological, socioeconomic, and political changes, where we sometimes even see black swans. So what should we do? There's been a recent paradigm shift in decision science community in particular to move away from predict then act paradigm. And basically there are some people in decision science who believe optimization theory and the notion of optimization is obsolete in the presence of deep uncertainties. And we need to move away to a more building resilience type of paradigm, instead of having a top-down approach, for example, to come up with a likely scenario for the future and then optimize the system to accommodate that best guess estimate of the future. The argument is to build a policy that is robust, resilient against the violations from any best guess estimates. So what if you can operate your system in a way that if the future deviates from your assumptions about it, you get less harm or least possible harm. So that is about building resilience and a bottom-up approach, and to basically identify vulnerabilities on the ground and then move back to the scenario space and see what kind of scenarios might cause those kind of vulnerabilities or possible failures in the system. And part of our research has been in that direction in the past couple of years, basically more scenario neutral approaches to decision making rather than scenario driven approaches. And so to come up with the strategies that works across a range of scenarios. So that is one idea. The other idea that I want basically end my presentation with is the ideas around leveraging the data science and machine learning. And as you might already know, data science and machine learning have been creating big waves in the society and also in the scientific community and in earth sciences and environmental sciences in particular. And there is a lot of excitement, sometimes overexcitement and hype around the abilities of these techniques in earth sciences and hydrology as well. So there is big potential there, and but at the same time, there are some possible issues that of overselling and what these techniques can do. Anyway, so this is an area that I'm quite interested in, particularly recently, and I think there is a lot of exciting stuff to be seen in the next few years around the applications and unleashing the potential of these techniques in our field. And what I'm showing here is just a bit of advertisement, a talk. It's about 1 hour long talk on deep learning, which is now the prominent machine learning technique that you might see out there, formerly called artificial neural network. Basically, deep learning is a special class of artificial neural networks and how they differ from our typical process-based mechanistic modeling paradigm, and if they are reconcilable. And also I'm showing 2 papers, one on, again, deep learning and how they can bridge into our physically based mechanistic process-based modeling. Also, there are some emerging ideas in data science around the notion of sensitivity analysis and how sensitivity analysis can help us better develop better models, more accurate models to predict or to simulate different processes and discover possible scenarios about the future, and also to support our decision and policy making. Anyways, I'm leaving you with those papers there, and I think that is all for my presentation, and thank you for the invite and attention.
Well, thank you so much, Dr. Razavi. I think it's very interesting, and yeah, so definitely this is after hearing your presentation, I feel I'm out of date engineer. I need up. But regardless, this is a lot. It's very good learning for sure. And now is thank you for this presentation. And now it's a question for folks to ask question. There's one comment from